Hello, my name is Tori Hale, and today I would like to discuss how I utilize the concept of entropy in the classroom, and specifically some examples that I like to use to help the students visualize and more accurately understand entropy and what it has to offer. Now, I love to begin with this concept of coffee. Not only because I'm a coffee lover, but my students love coffee as well. And as most high school students, hardly anybody drinks it black. So I give the example of creamer. And I like to pose the question, I wonder what is happening to the creamer. I wonder why it moves the way it does. It appears to only go in one direction in the sense of it goes from that more ordered state of where the creamer was to where it meshes out and spreads all throughout the coffee. And even if I don't have coffee lovers, think of a tire. Let's say you're on your way to school this morning to get the first period of AP chemistry, and maybe there's a slash in your tire. Why would the particles go from inside the tire and just move directly outside? Why would my ice cream that's naturally in the solid state melt to the liquid state? It appears that, again, they all go through some consistent way. It's not that, sometimes my ice cream magically turns from liquid into solid. No, it always goes one way, from that solid form and then melting to that liquid form. And why does that happen? And ultimately, entropy can explain a lot of that. Now, before I get into entropy, I love to introduce some key terms to my students. First of all, just understanding what the system is, the surroundings, and the universe is. Now, systems is the object being studied. It would be the chemical reactions that we're really thinking about throughout the process. And then anything outside of that system is known as our surroundings. Therefore, when we combine both the system and the surroundings, this is where we get this scientific term of universe. Now, there's multiple systems to consider. So you can consider an isolated system, a closed system, or an open system. Now, an isolated system, as you can see on the slide, there's going to be no exchange of energy and no exchange of matter. However, in a closed system, despite there being no exchange of matter, there is an exchange of energy. Now, we as living organisms, we're a part of this open system, where there's both an exchange of matter and an exchange of energy. So understanding these terms and the system being utilized, entropy by definition is this disorder of the components of a chemical system. So the chemical system that I'm studying, it's going to naturally turn to disorder. In fact, that's the second law of thermodynamics. Now, it's interesting to note, especially in AP Chem when they utilize entropy in formulas, that it is symbolized by a capital S. But let's get into some examples of entropy. So I mentioned earlier this idea of a tire leaking. Again, it's going from a state of order to a state of disorder where that gas is rapidly escaping and going all throughout the air. You think of ice cream. Again, it comes from a solid form of that colored ice cream, but then melts into something that looks a bit more chaotic. Now, our book has 3 excellent examples. They mention the tea kettle, as I'm sure you read. They mention the oxidation of glucose, how it initially starts with 7 molecules, but then again, disorder and chaos occur and it turns into 12 molecules. And then they give the example of something as simple as understanding information in letters and how that relates to entropy. Now, one great example I like to give my students is of just water, the ice form of water and the liquid form of water. Now, again, I said that entropy is this type of chaos, but a lot of times my students like to think that based off these pictures, they think ice is more chaotic. Therefore, ice probably has a greater amount of entropy, but that's not the case. Entropy is not just something we can visualize. And in fact, if anything, liquid water is the one that has the most entropy. And this really has to do with microstates. So microstates, again, is like an instantaneous picture. It's a snapshot, one arrangement of how this energy is utilized. And as you can see from the slides, ice is actually much more organized. It has very less entropy than a liquid form and the vapor form of water. Now, again, if you think of ice, it's not going to move as much, and again, it's much more organized. As you get to liquid water, it moves more freely. There's going to be a vast more amount of microstates available, and therefore an increase in entropy. And then, of course, vapor, gas bouncing off the walls, much more chaotic. But again, it may not make sense until you give them that example of water and they're able to really look at it at the microstate level and why, entropy does not always meet the eye. Now, my last example, and one that I love to give, is about campfire. Because when you think about a campfire, you start off with wood and gasoline, but ultimately, what's the end result? You have ash, you have the carbon dioxide being produced, you have gas in the air, and again, you come from this nice form of wood to ashes and gases forming. Again, that's an excellent example of entropy occurring because, again, you're going from a less chaotic state to a more chaotic state. So again, those are just a few examples I would use in regards to entropy outside of the 3 examples specifically that were mentioned in our book. It's an excellent topic that I love speaking with my students about, and hopefully it may give you ideas of how to implement some of these ideas in the classroom.